The grammar of graphics, it's an idea about how to layer your graphics so that you can better convey information to the end user. And it's called the grammar of graphics because just like the grammar of language, it's necessary to write well to be understood. It's necessary to think well graphically to be understood. Okay? The implementation of this concept of grammar of graphics is done in R with the package ggplot2. The GG in ggplot, there's also something called ggally, there's a bunch of gganimates, a bunch of GG packages. The GG in there stands for grammar of graphics. What's neat about ggplot2 is that it allows you to directly map data columns in your data set to specific visual display elements, like the size of a marker, the shape of a marker, the color of a marker, the position of a marker, and so forth. And you have access to a bunch of dials, basically, that allow you to fine-tune how the chart looks. What I really like about ggplot2 is that it allows you to think about the logical structure of the plot. You do not just randomly plot a histogram, you need to think about the histogram and the data before you plot it. And ggplot2 sort of forces you to do that. If you're going to use a ggplot2 object, you need to have at least two components to your call. There's going to be a ggplot call in which you specify what data set is being used, and there's going to be a geom call. Geom stands for geometry, that specifies what kind of chart you are looking for. There's other elements, the facets, which correspond to small multiples, how you want your coordinates to appear, the scales that you're going to be using, the labels that you're going to be using, the guides that you're going to be using, and so forth. You can use themes. There's a lot of other things you can do with it. But at its basic, most basic, you will have a ggplot call, which specifies the data set. Within that, you will have an aesthetic call, an AES, which explicitly maps the columns to the actual design elements, and a geom call, which chooses the type of chart. On the website, I've added, or I've given you a report which is about 60 pages long that has about 30 to 35 examples of charts produced with ggplot2. There's an accompanying RMD file, an R Markdown file on the website that basically runs all of these examples in R format, and you can sort of cut and paste the objects there, the code. There is also two other RMD files with examples. The first one shows you how you could still do some visualizations using base R. You don't have to go the ggplot route. There's another package as well that can be used for plots or visualizations in R called Lattice. In that RMD file, I give you examples of how you could use Lattice to do some plots as well. And there's another RMD file where I try to do some more sophisticated plotting. So I repeat the Gapminder file, or at least the Gapminder chart. I give you an example of how you could plot that. And there's a few like non-standard charts as well that I show you how to build very sophisticated plots with ggplot2, just to show you that it can be done. Okay, so if you're looking for examples above and beyond the examples I'm going to show you here, because the examples I'm going to show you are going to be quite small, take a look at the report with its 35 plus examples, plus the R files that show you plenty of examples. How does the ggplot2 syntax work? It's pretty clear. First of all, you need to have a data set in what is called a tidy format. A tidy format is just a weird way of saying every variable, everything you could be measuring only shows up in one column. So if you're measuring, for instance, the GDP, the life expectancy, the population, and the continental membership of a country, you'd have all your countries in one, in rows. And for each of these countries, you would have one GDP measurement, one life expectancy measurement, one population measurement, and one continental membership measurement. Now, that sounds straightforward, and how else would you present data? But what if you had this data, but for multiple years? Like, what if you had life expectancy for 3 years, and the population for 3 years, and the continental membership for 3 years, and the GDP for 3 years? Tidy data means that instead of saying, here's the GDP for 2012, here's the GDP for 2018, here's the GDP for 2024, you would have all the GDP measurements in one column, and you would add a year measurement that would tell you, well, which year you were actually recording. That's all a tidy set is. ggplot2 works with tidy data. If you're using the package suite called the Tidyverse in R, it is compatible with the Tidyverse. So that's another reason why we sort of like it. Once you have a tidy data set, your ggplot call has to look something like this. So ggplot, right here, you specify what the data is. Well, this would be the Gapminder data. So you put in the Gapminder, and then you specify what the mapping is. Now the mapping is given with an aesthetic. Aesthetic is written AES here, aesthetic. And that explicitly links the variable with the design element. So in this example here, what we're saying is that the X variable will represent the GDP variable. The Y variable will represent the life expectancy variable. The size will be given by the population variable, and the color will be given by the continent membership variable. Obviously, depending on the type of geometry you're going to use, you need to make sure that the variables you map to the various display elements, the aesthetics, are the right type of variables. Right? Your size probably has to be a numerical value if it's going to be ruling how big the markers are. You can't have categorical values in there. You cannot have negative values even, right? So you got to make sure that these things sort of make sense. Now, if you just drop data equals and mapping equals, if you just write Gapminder and specify the aesthetic mapping, ggplot will know what you're talking about. So it's still a good practice to write data equals so that we don't get confused, but in practice, you don't need to specify that one of them is a data set and the other one is the mapping. ggplot will recognize that this is what's happening. Okay. Now, before you specify a geometry, if you just run this call here, nothing will be displayed. Like, all this call does is it tells you what data set you're using, and it tells you how to map the various columns of the data set, or at least a subset of the columns of the data set, to the actual visual display elements. But until you've picked a geometry, nothing can be displayed. Once you pick a geometry, and you would do so using code like geom underscore, and then the name of the geometry you want to pick. So for instance, bubble charts, they're displayed or produced with something called the point geometry, geom underscore point. So there's a list, I'll show you some of them in a second, a list of geometries that exist. I think the last time I checked there was 30 some of them. We keep on adding new geometries to the list of geometries. But in order to see something, you need to choose a geometry. You need to choose a chart type in which to feed the data and the aesthetic mapping. Right? So here, the result of this should be that there's 4 bubbles, one for each of the observations. And its X and Y locations are given by the X and Y variables that you've selected, in which case, in this case, GDP and life expectancy. The size is given by the population and the color by the continental membership. Once you've done that, you will add scale choices and, well, you'll specify the types of coordinates that you want. In this case, we're going to pick Cartesian coordinates. So we should see something in an XY axis. And we're going to pick the x-axis. We'll want it to be scaled logarithmically. If you don't specify these things here, it is going to assume that you want Cartesian coordinates, and it's going to assume that you have a linear scale. Right? So you, technically speaking, you don't need to specify which coordinates you want if you just want them to be the default Cartesian coordinates, but it might not be a bad idea to specify it nonetheless. And if you want your scale to be measured logarithmically, you need to specify that you want a logarithm here. And then you can add some labels and some guides. You can add a legend, a title. You can do a bunch of things. And at the end of the day, if you do all of these chunks together, you will get a chart that looks like the following. And each country here corresponds to one of the entries. Now, we don't have names of countries in this chart, so it's a little bit hard to see which one is which, except it's not that hard. Right? We know that the size design element is map, or is the population. So the largest population entry should be the largest bubble here, while the largest population entry is this country in the second row. And we know based on this legend that the purple bubbles are European countries, so there would be these 2 countries, which means that the red one would be the last entry, and then you can distinguish between the 2 purple countries by looking at the GDP. The smallest GDP should be to the left. So this would be the first entry, this would be the second entry, this would be the third entry, and this would be the fourth entry. Okay, it's excessively simple. Once you know how to write these things, how to stitch these things together. How are they stitched? They're stitched with plus signs. So what's nice about the ggplot setting is that you can produce a chart without some of the bells and whistles, no frills. And if you want to add stuff to it, you just need to add, literally add with a plus sign, specific frills, specific elements. Just a thumbs up or a response online. How many of you have used ggplot2 before? Kim? Okay, I see a few people with names. Not that many. Hang on, perhaps I need to make my screen a bit bigger to see a few more people here. Anyway, some of you have used it. That's great. If you have not used it, Christy, I see you use it as well. If you have not used it, now is the time to, to get familiar with it. Okay? This is going to be an excessively useful tool for you to master for your employment options down the road. Okay? Because it's going to allow you to produce charts that are very neat. And we know, at least we've talked about how it's much easier to convince your audience if your charts look neat and if they do not look neat. Okay? So you will take the time here to learn about this. For your project, you don't have to use ggplot2, obviously. You can use other things. And there are other things you can use, other tools you can use. But ggplot2, for my money, the learning curve is not that steep. It's a pretty simple learning curve. And once you have the basics of it, the quality of the charts you can produce is like miles above what you can produce with SAS or with Excel or with Python. Now, Python, you can produce nice charts as well. As just the amount of work to get there is much, at least in my mind, much bigger. So this is the most economical way to produce good charts in a short amount of time. Let me reiterate, until you've selected a geometry, you're not going to be able to see anything in your charts. I wrote there are currently 37 available geometries. That was when I made the slides. There are more than 37 available geometries, I promise you that. Some of the useful geometries, if you go look in the report that I wrote with a sign, we list some of them, like the scatter plots, the histograms, the line charts. It's pretty straightforward. There's a table that basically lists a lot of these geometries. So please take a look at that report so you have access to a larger sample of geometries. Let me show you how that would work in practice now. Here's a piece of code that's going to use a data set which comes with the Lattice package. So it's a built-in data set with a package in R. You have to have installed Lattice and ggplot2 for this to work. And if you look at the actual code here, what you're seeing is that we're using a data set called Singer, which is right here. If you wanted to know more about this data set, you could load it in R and just explore it, but we're going to be exploring it with ggplot here. I happen to know that one of the variables in there is called height, so I'm going to map this variable to an x value. And I'm going to create a histogram. So my first bit of code specifies the data set and specifies explicitly which variable is mapped to which design element. In this case, the x value is going to be given by the height of the singers, and I want the outcome of that to be a histogram. So what do we expect to see here? We would expect to see a histogram of the heights of singers. And sure enough, this is what you get. It's not a super nice histogram. Here I've added no bells and whistles at all. I just got the default histogram output from such a call. You would be able to go and specify the bin width and specify the colors and specify a number of other things with that. Okay? But I'm not doing that at the moment. Look at the second call here. It's the same setup. I specify the data set, which is going to be still the Singer data set. Now I explicitly specify the variables that get mapped to two different design elements. The height used to be the horizontal variable, and now it's not horizontal anymore. It's going to be the vertical variable, the y, and the horizontal variable is going to be the voice part. And eventually I will produce a box plot out of this. Well, in order to make sense of this call, before we even see the outcome, you need to have a clue as to what the variables mean, right? In the Singer data set, the height is the height of the person. That's fairly straightforward. The voice part is, well, what role they play in the choir. Which choir? Specifically the 1979 edition of the New York Choral Society. So there's people of various heights in this choir, and they don't all sing the same parts. There's 4 parts that could be sung: alto, bass, soprano, and tenor. Right? These are the types of parts. So what we would expect to see here is a distribution of heights per voice part. And the type of plot that we will have for these would be box plots. So if you put that together, you would expect to see a different box plot for every voice part. The voice part is categorical, it's a factor level. So there should be one per voice part. It turns out there isn't 4 voice parts, there are 8 voice parts, because your voice parts, bass, tenor, alto, and soprano, can be split into 2 types each. And if you look at this, what you're seeing, this is the neatness of the graphic, is that the bass parts tend to be sung by taller people. This is the height here, taller people. The soprano parts tend to be sung by smaller people. That makes sense. Sopranos are usually women or young boys. And on average, you'd expect these people to be smaller in a larger population than the bass voices, which are usually sung by big hulking men, so they can sound like this. Right? I mean, the voice level isn't always correlated with height, but it often is. In fact, this is what this chart is showing us here, at least in that specific population, the population of singers in the New York Choral Society. The lower voices were sung by taller people, and the higher registry parts were sung by smaller people. Okay? But the key takeaway here is that, remember, Y is the height, what we're trying to measure, X is the voice part, and it automatically filters the data, only keeps the points for each voice part in the data set, and basically creates a box plot out of those points, under these filtered observations. There's other things you can do here. I'm going to show you that if you wanted to, you can layer multiple geometries on the same chart. So we're going to use a different data set, the data set of salaries in the package car. So you'll have to load this package. You'll get access to the data. I'm just going to give you a bit of information about this data set. It's salaries for a sample of university professors in the States. But I wrote 2018-2019, that's a typo. That was from 2008 to 2009. And here are the variables that you can find in there. There's the rank of the professor, the sex of the professor, the years since they've obtained their PhD, the number of years they've been professors, and their actual salary. Now you can probably guess that rank is a categorical variable, but it's ordered, right? There's a hierarchy, there's a path you travel until you become full professor. So even though it's categorical, it's really an ordered variable. Sex, that's a flat-out categorical binary, at least in that data set. Years since PhD, numerical. Years of service, numerical. Salary, numerical as well. Okay, so we have 2 categorical variables here and 3 numerical variables. So we're going to create a chart here. The data set will be salaries, and we will explicitly map the salary to the y-axis, the vertical axis, and the rank, what kind of professor level they are, to the x-axis. So depending on how many ranks we have for professors, we should be seeing a different distribution, a different chart for each of the ranks, right? Because rank is categorical levels and the salaries are numerical. If X was a numerical variable instead of a categorical variable, then we would expect there to be a spread and not 3 separate objects that get mapped. Okay, so that's the ggplot call. Then we need to select a geometry, otherwise we're not going to see anything. Well, we're going to add 3 geometries, in fact. We will have a box plot geometry first of all. So that means that the objects that we will be plotting, one for each rank, will be box plots. Now you might have noticed in the previous slide that when we call the box plot, there's no option here. We box plot and then an empty set of brackets. You can have options within a box, within a geometry. So you can specify that you would want, for instance, the color of the box plot to be cornflower blue. Now it's not the color here, it's the fill, but it's going to fill your box plots using a color called cornflower blue. And the actual color is the outline. So fill is the inside, color is the outline, and this one we'll pick to be black. And I'm also adding a new option which is available in boxplot called notch. I want my box plots to be notched or belted, sometimes it'd be called. If you try to use notch equals true as an option to a geometry that doesn't accept notch equals true, it will spit out an error. So you need to know the options for each of your geometries. These are the specific things that you can modify for each of the geometries. So in the box plot, there's at least 3 things you can modify. You can modify the fill, you can modify the color, and you can modify the notch option. So that's going to be one thing. We're going to be giving a box plot for each of the ranks. Then we're also going to add to that a point geometry. Remember, we used the point, or we saw the point before when we talked about the Gapminder example up front. And the point geometry is basically a scatter plot. So what's going to happen here is that we're going to superimpose the actual measurements of the salary on top of the box plots for the salary. We'll do so using the following options. The color will be blue, so the points that we add will be blue. There's a position equals jitter option. This option is chosen or selected so that the points don't all overlap on top of one another. So we're going to give them a little random noise so that we can see the extent of the distribution of salaries. And an alpha of 0.5, alpha represents the transparency. So it's not going to be completely covering what's underneath it. And the order in which we add the geometries matter, right? ggplot's going to first layer the box plots, then on top of that it will layer the point geometry. And we're going to add a third geometry, which is called the rug. I won't talk about it now. We'll try to see what it looks like or where it's found in the actual display. So this is what you would expect to see by calling this ggplot call. There is one box plot for each of the ranks, and you see the ranks here are assistant prof, associate prof, and prof. We're seeing box plots for each of them, but we're also seeing a cloud of points. Right? So these are all the potential salaries for the associate prof, all the salaries for, assistant prof, all the salaries for the associate profs, all the salaries for the full profs. Is there anything else that we can see here? Remember, when you're thinking about the multiple eyes, it is not sufficient to just plot the data. You would think about what it is that you've seen. And what you seem to be seeing here is that as profs move up the ranks, as they go from assistant prof to associate prof to full prof, their salaries increase. Well, that's not surprising. That's what you would expect to see. But it's nice to see that your chart actually agrees with your intuition here. There's a few other things you might notice. There's a fair amount of variance in these salaries. There are some assistant profs who started with higher salaries than full profs. What could be a potential explanation for this? And that's the kind of stuff I want you to get into the habit of thinking. We can provide potential explanations without knowing if we're right or not. The data doesn't give us a proof that we are right about our potential explanations, But we can start thinking, what is it that would make these assistant profs here make more money when they're starting than full profs here? Well, it could be that they work at a more prestigious university. Perhaps one of those is a Harvard assistant prof, and this person is, I don't know, teaching at St. Lawrence College in Albany, New York State. Who knows? But that's a possibility. Another thing you'll notice, there are some values here which are like flat out huge salaries for full-time profs. There's at least 3 of them which are even considered outliers by the box plot algorithm. Now remember, the box plot algorithm recognizes things that are outliers, assuming that the underlying distribution is normal, and it's not clear that this distribution is normal. It's normalish, but it definitely feels as though there's a larger tail here than on the other side. So it doesn't even appear to be symmetrical, at which point you might doubt the assumption of normality, which would make you doubt whether you recognize these outliers as true outliers. But there's definitely 3 profs here who are making like gigantic salaries in US dollars. That could be worth exploring further. You can say, well, how is it possible that profs can make so much money? Look, we might be talking about Nobel Prize winners here. Right? And then you can also wonder about this person, this point, who is a full prof and who makes less money than everybody else, including assistant profs and associate profs in this data set. Again, you can come up with a potential narrative, a potential story. We have no way of verifying if this is the case or not unless we dig in and try to find information outside of the data set. But it's easy for me to imagine somebody who's soon to be retiring, or who's been doing what they like for years, and they want to try to free some money for some of their newer colleagues. That could happen, right? And so they're willing to accept a smaller salary to be a prof than some of the newer up-and-comers. The last item I'm going to show you, we're seeing this weird display here. This is the rug that we were talking about. The rug will tell you exactly where all of the measurements are found if you aggregate everything. So this is a rug for all of the salaries combined. So you're basically projecting, we chose the side to be the left side because that's the one that made sense. That's where our numerical variable was. We're projecting everything down to the rug, and that gives us an idea. The concentration of salaries is roughly speaking here for these 3 categories. And there's a few outliers in this direction and a few outliers in this direction. Okay, so it's fairly easy to create layered graphics. You can add a fair amount of information. So that's for the geometry. The aesthetics as well, let's talk about those a little bit. What can you put in your aesthetic functions? Do you remember perhaps last week or 2 lectures ago, I showed you a chart, a black and white scatter plot that sort of looked like nothing, and then we switched over to a color version of it that had different shapes and different sizes and different colors. That was a slide where I was talking about the types of chart design elements you can add. These are the things that you can actually specify with the AES mapping, the aesthetics mapping. They will map various variables to an attribute of a marker, and they will generate a corresponding legend. If you have the X and Y aesthetics, the legend is actually written on the chart itself. It's the ticks of the values. Every other type of thing which can be specified with an aesthetic mapping has its own legend. The size, the shape, the color, the transparency, although you don't usually add the transparency as a legend. But everything which can be specified in the AES has a scale, has a legend, which you can choose to display or not. You can specify the aesthetics within the data function call, the ggplot call, or you can specify it within the geometry. When you specify it within the data function, it applies to all of the geometries in the charts, all the layers that you're adding. If you specify it only within the geometry, it only applies to that specific geometry. Each geometry has a different set of aesthetics that are available to it. The scatter plot geometry, the geom point, has these specific aesthetics: X, Y, alpha, color, fill, shape, and size. Well, there's also transparency, but I'm not really adding it in there. That's an option for the geometry, not an actual aesthetics option. Sorry, I misspoke here. So you could, in theory, have a 1, 2, 3, 4, 5, 6, 7-dimensional data set expressed by a point geometry. They have to have the right types of variables. Obviously, you couldn't use the shape. You could not use a numerical continuous variable for the shape, right? It's got to be a specific category or specific integer on a small list of integer. The size has to be a positive value. The fill has to be, well, the fill could be continuous or categorical, actually. Same with the color, assuming you have a gradient of colors. Alpha, that's the transparency. X and Y could be numerical or factors depending. Now, there's a pretty important difference here. If you're trying to specify characteristics like color and shape, and you do so inside or outside the aesthetic function. If you do it within the aesthetic function, you basically have to map the color and the shape or the fill or whatever to a specific variable name, and then the value of that variable for that specific observation will decide which color, which shape, whatever is assigned to the marker. If you specify the characteristic outside of an aesthetic call, by that I mean you literally specify what color you want or what shape you want, then these things are not mapped to the data. They will be the same for every point in your data set. Let me show you an example of what I mean here. The first chart here will use the MPG dataset, which is built in the ggplot package. So we're going to plot the MPG dataset, and we're going to use two variables, CTY, which stands for city, and HWY, which stands for highway. So city and highway, these would be the city mileage and highway mileage, basically the fuel efficiency of the car in the city and the fuel efficiency of the car on a highway. So these are the aesthetic mappings that apply to every geometry in your chart, in your plot. And then we add to that a specific geometry, the point geometry. So we're going to plot a scatter plot, and we would like the color of the points that show up in this plot to be mapped to a variable called class, and class is one of the variables in your data set. So you at least had city, highway, and class of vehicle. What we would expect to see here is a scatter plot with different colors for a point based on the class of car that it is. So let's take a look at this. This is indeed what you see. A scatter plot, city mileage, highway mileage, and different colors based on the type of car that you have. And one thing you're noticing, right, when you put your multiple I hat on, is that there's cars of contiguous colors and regions. So we have a lot of these pink cars here, the SUVs in the bottom right, and we have some magenta subcompact cars top right. We have some compact cars as well top right. Right, so the colors, the class seems to be a good indicator of what the city mileage and the highway mileage will be. There's a relationship between the color and the mileage. That's what you see from this chart. And another thing you might notice, again with your multiple I hat on, there's a, roughly speaking, a linear relationship here between the city mileage and highway mileage. If your car guzzles a lot of fuel in the city, it's also going to guzzle a lot of fuel on the highway. And if it doesn't need that much gas in the city, if its mileage is more efficient, if it can go further with 1 liter of gas in the city, it can probably also go further with 1 liter of gas on the highway. Now this is just a map of mileage in the city and the highway for one car. We don't know how people got these measurements. Like, did they just follow one person driving all of these cars around? Or is it various people or averages? We don't know any of these things, right? So the data the chart is only as good as the data and our understanding of the data. We also don't know if these measurements are true. Like, who gives these measurements? Are these reported by the manufacturers, or is there some agency that tests them? If they're reported by the manufacturers, it's easy to imagine that they'll pretend that you can go much further with 1 liter of gas than you could, just to make it sound as though their cars are more efficient than they really are. If it's tested by some agency, then presumably all of the cars are tested in the same way. And so even though there might be some noise, even though there might be some individual differences within the cars of one make, these differences probably wash out if you try out enough cars in enough makes, and you can probably trust the results. But this is not information that you can arrive at, or conclusions you can arrive at just by looking at the chart. The chart only allows you to ask questions about the data set. Now, perhaps you look at this and you'll say, come on, this is a stupid data set. Who would think of asking these questions? What I'm trying to point out here is that no matter how stupid the data set is, no matter how silly the display is, the multiple eye framework says, let me try to figure out what's really happening here. I might be completely wrong with my hypotheses. I might miss the boat entirely. But I should be able to ask questions and to come up with potential answers, or potentially to say, you know what, I don't have enough of an intuition to be able to answer that question, or to be able to ask questions. I should work on developing the intuition, or I should go online or ask my subject matter experts if I can, if they know how to answer questions like these. This is why data visualization is useful, because it leads to questions. At least it should lead to questions. Like these examples of visualizations I'm giving you right now with ggplot2, they're like the classical examples. These are these pedagogical data sets that people use to try to show you how ggplot works. And sure enough, I think this shows you how ggplot works, at least at some level. But I do want you to get into the habit of never just looking at a visualization and saying, that's that. Right? There's always more that you're trying to uncover. You are trying to understand the data set as a whole. You're trying to understand the situation. You're trying to question how the data was collected, whether you can draw any useful conclusions from it or not. And if you can draw a conclusion, can you only apply it to the sample that you have in your data set, or do you think it's applicable to some larger population? These are the types of things that I mean when I talk about using the multiple eyes framework. So I've shown you here how you can specify an aesthetic within the geometry call. Let's see what happens if we specify the color here, but outside of an aesthetic mapping call, inside the geometry call. So we have the same type of plot. We're plotting city mileage, highway mileage. But now the color isn't going to be mapped to the class. The color is going to be a specific color, red. What you would expect to see here is that every point is going to be red. Right? If you need to specify a name or a shape or a size, you do so outside an aesthetic mapping. If you want the characteristic, the size, the color, the shape, to potentially vary from one observation to the next, it needs to be placed inside an aesthetic mapping. Right? So you would use a call like this one here when you're just trying to change what the chart looks like. You don't like the default colors that ggplot is giving you, and if you're trying to come up with a relationship, a multivariate relationship between, say, more than these two x and y variables, then you would put things inside an aesthetic mapping to see if there's a relationship between the class of the vehicle and the mileage that it has, both in the city and on highways. And that is, roughly speaking, everything I'm going to tell you about ggplot2 here. I don't want to spend too much time explaining how it works. I think the best way to figure out how it works is to try it out yourself. Now, I've given you, as I said, a number of examples in these R Markdown files in the report. And it's not a bad idea, of course, to take a look at these examples, to try to build up your confidence with the actual package. But I think it would also be beneficial for you, if you're not completely familiar with ggplot2 now, to think about what you want your chart to look like first, to draw it down, with a pen and paper, to have a bit of an idea, then to try to create the chart that you're planning to create with ggplot2. And if you're new at this, you're going to fail. Like, you're not going to be able to get all of the elements. And afterwards, then you go and you look for examples that did something like what you tried to do. And then you can modify your attempts. That makes more sense to me in terms of trying to learn how to use ggplot2 properly than to just copy and paste examples and to try to modify someone else's example to fit your data and your context. Okay. I can't force you to do it this way, obviously, but I would advise you to really take the time to design your charts first, then afterwards to try to create these charts. With ggplot2 or with other tools. It doesn't have to be done with ggplot2. If you've come across nice examples of charts when you do your researches, you could post them on the Slack channel as well, so that everybody can see, oh, I found this nice chart and I found this nice piece of code that allows me to do that, or I've created this and I'm happy with it, and there you go. I might, once you provide me with your charts for the projects, I suspect I will put the nice ones into some sort of a document, and I can make those available to the class afterwards, so you can see what your classmates did. I won't write your names on them if you don't want me to write them, but you can see what your classmates did, and you might get some ideas for other projects or other charts down the road for yourself. The other thing I'm going to say is that once we're done with the visualization module, I'm going to expect that in the future projects, when you have to do a visualization, you will still try to produce or to give me nice visualizations, not dinky, out-of-the-box visualization, right? So this is a skill set that you will be building on, and you'll practice it by trying to come up with nice charts in your other projects as well. One of the ways in which the multiple eye hat is easy to put on, that you can easily talk about multiple eye things, is by looking at visualizations. It's easier to interpret a visualization than it is to interpret an actual table of data or an output for some analytical package that you use in R or Python or what have you. Right? So that would be a good practice for you to practice. Okay, this is what I want to say about ggplot2. Let's talk about dashboards a little bit here. I don't know, is anybody familiar with the software Power BI? Give me a little response, a thumbs up, or some sort of emoji if you've used Power BI. Christy, you've used Power BI. Has anybody else used Power BI as a tool, a dashboard tool? It's a Microsoft product. S.C. Smith, of course, yes. It's a Microsoft product, and you have the ability to download it online for free. I will not be showing you how to use Power BI. Perhaps some of you have heard of Tableau instead, or worked with Tableau instead. Dashboards are or Power BI, which is a way to implement dashboards. They're basically the tools that people in the non-academic world use for visualizations. If you try to teach ggplot2 to accountants or to public servants, they're not too keen on it because eventually they have to produce a dashboard, which is often going to be, as I said, implemented in Power BI, that goes right to their bosses. And their bosses are used to pie charts and to gauge charts and to various types of non-academic charts, if you want. And it can be difficult to convince them that there's value in using something other than Power BI as a tool to display this information. Now, as it happens, you can integrate R charts, ggplot2 charts, within Power BI. And so all I want you to know here is that if at some point you encounter somebody who insists that you do work with Power BI, well, you can do so. You can set up, it's fairly easy to set up a baseline dashboard in Power BI, but then you can still import some charts over which you have total control through the R import button from Power BI. If anybody's interested, I do have some documentation in the supplementary material about dashboards and a few examples in Power BI as well that were written by a former student in this class. I will not be talking about Power BI as a whole, but I want you to be aware that there's a way to incorporate R and Python charts, of course, within Power BI. I'll only say a few things about dashboard. In fact, there's a good chance we'll finish the dashboard lecture today, and then we'll move on to Bayesian analysis when we meet on Wednesday. In a non-academic world, the quality of an analysis that you run is limited by how well you communicate it, how well you can deploy it. You can have the cleverest take on a data set, the cleverest analysis, but if you cannot communicate that to your higher-ups, to the director, to your bosses, nobody's going to take the insights that you've generated and turn them into something useful. So as a non-academic person trying to convince people of the value of analysis to make decisions, you have to find a way to affect the reporting of the results, to be in control of the reporting, to be able to tell people things that they will understand in a manner that they will understand. And that usually means having a good understanding of how reporting is done in your company or your department. Who will be receiving the reports? That's something you need to know, because you need to be able potentially to fine-tune your reports with that person in mind. How are the workflows deployed into production? So if you come up with an idea that's going to help people get insights from data, how do you go from the data set that you're analyzing to presenting the insights from the analysis to the higher up? How is data and how's the work pipelined? How does it go from point A to point Z? Because that's going to help you decide if the insights you get can actually be turned into policies that are useful. Now, very often in companies, people will start automating the reporting. They'll have gone through the data set collection a number of times. They'll have gone through the analysis that you run, and you'll write code that basically allows you to do these things automatically. And then they'll have these automatic pipelines that take your analyses and feed them into a dashboard. And so at some point, you don't even need to be part of the process anymore. Data is collected, you press the button, get fed into your analysis software, and the outputs get fed into a dashboard software, and that goes right to the higher ups, and you're out of the process. If your company has an automatic pipeline, you probably want to make sure that it is audited and validated regularly. Very often things change in the data collection process, not just in terms of how you collect the data, although that can also happen. You can go from, say, paper collection to digital collection, or switch from one digital tool to another digital tool. But there could also be shifts in the trends in the data that you collect. And it's conceivable that your analysis was making implicit assumptions about what the data coming in was going to look like to run some analyses. For instance, it might have assumed that the underlying distributions were normal. And it might have been the case when you first started collecting the data and you did a few tests for normality and that you were pleased that it was normal and you just automated your code. But it's conceivable that things change in the world at large, the world that you're collecting data from, and now the normality underlying assumption isn't valid anymore, and the results that you are producing are hogwash. Right? So you need to be able to stop the automated process, in the sense, to audit it, to verify that the assumptions that you built in are still valid. Because if they're not, and things come out automatically, well, the problem is that people trust intrinsically what comes out of these algorithms, right? So they will not look at what's happening in the process, in the pipeline. They'll just be happy with the result at the end of the pipeline. It is very important when you report, when you deploy your work, to keep communication lines open, and you should do so at various stages of the project, not just once the project is done. In the Intro to Quantitative Consulting course that I teach, one of the main things that we focus on is the constant flow of communication. If you're going to be late with an analysis, we need to know ahead of time so we can take measures to mitigate the effect of being late. If it turns out that what the client was looking for isn't going to be feasible, we don't wait until the end of the contract to tell them. We tell them as soon as we can. Communication lines have to stay open. Ideally as well, you would use a software to produce a report at the end of the process, which would be the same software you use for the analysis and for the data processing. It makes it easier to build all the pieces of your workflow, which will eventually be automated, but it also minimizes the amount of error related to cut and paste. If you have to take the output of one software and then basically manually input it into another software, there's too many ways to make mistakes there. It is also easier to share the work with another project member if everything takes place in the same universe, software universe. Some people will tell you that one way to simplify the process even further is that you should deploy to the web directly rather than deploying to some dashboard which will sit on someone's desktop and that you might not have access to it. So deploy it to the web. Everybody who's supposed to have access to the report will be able to have access to it. When I speak of reports, well, I usually mean, or most people usually mean, a dashboard. Some sort of visual display which is used to monitor conditions and to facilitate understanding. And generally what they mean is some sort of a horizontal display where you have a number of charts, which could be produced with ggplot2. Conceivably, you might have more than one page, so you can imagine a series of monitors that have a series of charts on them, and people would be trained to read the charts so that as soon as something goes into the red, we're noticing that something is wrong and we need to sound the alarm. Dashboards don't have to be that modern and that complicated. Anything which is a visual display of data that can be used to monitor conditions and to help people understand how their system is working, that's a dashboard. So it could be one of these funky interactive displays that allows people to sort of slice and filter data and dive in, like you would see on CSI or some of these modern TV shows. Or imagine something like Tony Stark in the Avengers, right? It could be something modern like that. But it could also be something as simple as a little PDF document that shows you the value of a few key metrics. Or a screen, a wall-mounted screen that nobody can play with. You're just seeing what's out there. If you've ever taken the O train in Ottawa, well, you know, the little display that tells you when the next train is coming, you don't have access to that. You can't change things around. You just wait until the train comes, but at least you have some way to monitor the situation, the condition of the system. It could also be something you put in an app that can be read by a phone, or at least that you could view on the phone, so that you can on the fly figure out what's happening. There's many ways to display that type of information. It's called a dashboard because, well, by analogy with a car's dashboard. I don't know how many of you are habitual drivers. If you drive, or if you've driven before, you know that most of your attention should be kept on the road and the vehicles that you're sharing the road with, or the people, the pedestrians that are potentially wanting to cross and what have you, right? But at the same time, you are in charge of a machine that might, work well, great, or not work well. And how well the machine works, or how badly it works, might affect your ability to stay safe on the road. So there's competing needs. On the one hand, you need to stay safe by looking what's happening. At the same time, you need to make sure that your car is not about to break down and then cause problems for yourself and for the other people that are driving the roads with you. So the dashboard, the car dashboard, is a way for you to monitor your driving situation at a glance without having to spend too much time trying to figure out what is happening with your car, with your mechanical car, right? Because most of your attention should be spent on other things. And that's basically what a dashboard is. It's a series of lights, of flashers, that will tell you at a glance if something is not going right. Right? It isn't a tool where you're expected to sit down and stare at it for hours until you figure out that something isn't right. It's something that you should be able to use very quickly to recognize when something is not the way it should be working. And this is why we call it a dashboard. It has the same role as a car dashboard. There's a number of questions that you should answer before you design a dashboard. These are multiple eyes questions. Who's the consumer of the dashboard? Who's going to use the dashboard to monitor situations? What story should the dashboard be telling? What data categories will be used? What is going to appear on the dashboard? If you have 50 charts on the dashboard, you probably have killed your chances of being able to tell what happens at a glance. So you have to have a minimal number of charts. You still need to be able to tell the story, but in a way that will be able to be parsed. Too much information destroys the purpose, which is to help people monitor situations at a glance. Now, you might want to have various dashboards for various people, and they'll all be monitoring different components, so you might be able to get away with 50 charts. It's just that they've been distributed to various users, and not every user, or none of the users get the full 50 chart. They just get a smaller subset, something they can work with. Finally, how can the dashboard actually help the consumer? So you need to have an idea as to what the consumer of the dashboard's goals are. And if you don't know what their goals are, you can't help them well, you can't help them craft the story that the dashboard is supposed to tell, but also you won't be able to help them do something with it. In practice, I'm not going to go through these rules here, but in practice, what it means is that you want dashboards that are somewhat minimalist, that don't overflow you with information. This is the dashboard from the city of Edmonton in Alberta. At least it was a dashboard a few years ago when I did a screenshot. You had a number of possible categories, and in each of these categories you had projects that the city had embarked on and they wanted to report to the population. And then you had a little color scheme that told you whether something was, we're still collecting data, something we're still measuring, whether we were happy with the achievement or not, whether something needed improvement, whether we were close to the target, or whether we met or exceeded the target. And at a glance here, people could see, at least the citizens could see, that the travel time and reliability of the transportation system had achieved the goal that the city had set, whereas the transit security had not. There were too many accidents, or too many incidents, I should say. Right? And you could do this through all of the various projects that the city had in mind. It's a very simple bit of information. There's barely anything. We just have a color element, a number that goes with it, and a tag that tells me yay or nay, roughly speaking. An easy way to convey information. From a stylistic perspective, if you're going to be producing dashboards, one of the suggestions we have is that you should try to stay very minimalist, as I said, not too many colors if you can avoid it. So I like this one, white, gray, blue. Not too many charts. Like this one only has 5 charts, basically. A lot of white space. This is interesting to me. What it means, well, this specific dashboard is a way to represent how course evaluations at the university, I think it's the University of Cincinnati, if I'm not wrong. Yeah, University of Cincinnati course evaluations. So every prof would have access to something like this. One of the lessons here is that if you use Power BI, you can, presumably modify a lot of these external parameters. In ggplot2, you might not be able to, not to the same extent, although you can. It might be more difficult to set it up so that all of them fall nicely where they should fall with the right kind of minimalist design. Very often you will produce the ggplot2 charts so that the graphic designer will have a clue as to what the chart will look like, and then somebody else is going to come in and basically cut and paste everything into a nicer format. So when you produce your charts for me, you might use some specific themes that look, better, but you might also basically cut and paste documents, cut and paste graphs. I'm not asking you to only ever use ggplot2 or R or Power BI or whatever tool you use to produce a visualization. You might need to use some graphic design, graphic manipulation programs to make your thing look better. And that's okay as well. All right? You don't have to just stick to the output of ggplot2. You can modify the output. Most people who do visualization also have Adobe Acrobat, I don't know how to pronounce that one in English, or Illustrator, or potentially some GIMP program, or some other software that allows them to manipulate the images and to make it do or say what GIMP or what ggplot2 alone cannot actually say. So keep these two in mind as examples of good dashboards, because we're going to see some other dashboards which are not necessarily going to be as pleasant to the eye, as useful. You want to avoid things that look like this. Way too many colors, way too many charts. What the heck is going on here, right? And then nobody can look at this at a glance and get a sense of what's happening. So our charts, if we're producing individual charts for people to look at, we want things that will reward pre-attentive processes and attentive processes. Something you can see at a glance and something you have to dig deeper to get a good sense of. That's good. For dashboards, this is not the time for people to have to dig deep. They should be able to see at a glance what's happening. You do not want to distract people with too many colors, too many charts, weird background colors. This isn't going to be useful, right? So you want to avoid producing something like this. Better to have multiple pages and to lighten up the load, to try things other than pie charts if you want, if you can. Here's another example of what a priori looks like an interesting dashboard, but that's not a good dashboard. Like, what are these things here? Why do we have none of this makes any sense? So you want to avoid producing things like this or this in favor of things that look like this or this. All right, I'm not talking about dashboards more than this. This is perhaps just, I don't think for the project you should be producing dashboards, by the way. I mean, you can use Power BI if you want to have 1 or 2 charts, but this shouldn't be your focus for the project. But outside of academia, outside of school, the way that people usually provide information is with dashboards or through dashboards. So you should at least be aware that they exist. And when the time comes and you have to produce a dashboard, you should definitely consider minimalist dashboards. Focus on the stuff that needs to be seen quickly and be careful with the colors and the amount of charts you put on these things.